This is Free-Range Digital Design Foundation Modeling. This is Chapter 4, first of 2 videos. What we are doing here is developing some background for digital design. We're still about 2 chapters away from doing actual digital design. But what we want to look at here is common number systems associated with digital design. Additionally, primarily one of the main number systems associated with digital design is binary, and those binary numbers have certain important attributes that we want to express. And lastly, we'll finish off with some engineering notation. Numbers. So why do we have numbers? Essentially so humans can keep track of things. So I can remember in 8th grade my teacher told us about a number system used by a primitive culture, which was, they had 3 numbers. It was 1, 2, and many. So I always use the example here of that. We have a little box here, so how many dots does that have in there? You can look at that and say, well, it has 1 dot in it. So draw another box here. How many dots does that have in it? Well, it has 2 dots, obviously. And lastly, I can draw another box here and many. Okay, you can count them, but you'll need a number system to count them. That's the motivation for number systems. One advancement in number systems was Stone Age unary. It's something that we still use today. This is the classic Stone Age unary system here, where we use these little slash marks. So this number is equivalent to 12, base 10, which is decimal, what we still use today. So still commonly used today, really primitive, but then again, very useful. Once again, we are limited as humans and what we can keep track of in our brains, so we develop number systems to help us keep track of that. So numbers systems here, they have just certainly definitions that you know and love. Probably not. I mean, you can work with numbers without understanding this stuff, but it's good to know. So a number system, it's a bunch of it's an ordered set of symbols. It has some mathematical operations defined on those. The symbols that we're working with are, of course, digits, and for decimal, that's 0 through 9. Mathematical operations, we all know those: plus, minus, divide, multiply. So the radix is defined as the number of symbols in that ordered set. As you know, decimal has 10 symbols. There are not 0 through 9. We'll be working with binary, which has 2 symbols, and then also hexadecimal, which has 16 symbols. So number is defined as a collection of digits. It can have 2 parts. It can have an integral part and a fractional part. Those parts are divided by a little dot that we generally know as a decimal point because we use decimal, but it's actually a radix point, which is associated, the radix is associated with whatever number system you're working with. So the radix system, once again, is used to delineate the fractional and integral portions of the number. So here's the standard number format. This is right here is the integral portion. This right here is the fractional portion of the number. What we have here is these little subscripts represent, essentially you're going to see it as being a weighting. So each of these A's here are digits, but depending on the position of that digit, there's a different weight associated with that digit. So the whole number here, the fact that the weighting on that digit starts at 0, next digit starts at 1, this is all arbitrary. It's done by convention. What else do we have in this thing? R is the radix point. For decimal, it's 10, of course, but if we write a number and leave out this radix, this little radix subscript, it's interpreted as 10 decimal. So if we're working with a number system other than 10, we always have to include that radix. So this number, this digit right here, is defined as the least significant digit. This number right here is defined as the most significant digit. So once again, to get useful number system, we are going to put these digits side by side, which is referred to as juxtapositional notation. So once again, each digit has an associated weight with it. The weights are integral powers of the radix, as you saw in the previous example. So, for example, 987 here is actually which is a decimal to decimal conversion, which essentially does nothing. But in this binary number here, we know it's binary because it has a radix of 2. We actually can use this type of approach to convert this binary number to decimal. So this binary number here is going to be 1 times 2 to the 2 plus 0 times 2 to the 1 plus 1 times 2 to the 0 plus 1 times 2 to the minus 1 plus 1 times 2 to the minus 2. So this equals, this is 4, 0, 1, 1 half, 1 quarter equals 5.75. Okay, that's an official binary to decimal conversion. We'll hit that a little bit later also. So these are the 3 digital radixes or radii we're going to work with in digital design. Decimal, because we're humans, that's what we understand, space 10. Binary, that's what the hardware understands, it's base 2. Remember, transistors are either on or off. And once again, we bring in hexadecimal, which is base 16. That helps us deal with binary. Binary generally has a lot of strings, long strings of zeros and ones. Using hexadecimal allows us to reduce some of those long strings of ones and zeros. So we need to be able to generate the binary sequence of numbers, and the important sequence is binary numbers 0 through 15. It should be not 1 through 15, but there's a little trick to generating these, so I wanted to show you the trick. To generate these numbers, which you'll have to do initially, but you're going to memorize them very quickly. You go 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1. This is the least significant bit, and what I'm going to do here is move over 1 column and go 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Use that trick again, move over a column, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Do a trick one more time, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1. Okay, so those are my binary numbers, 0 through 15, which corresponds to hex number 1, 2, 3, 4, 5, 6, 7, 8, 9. After 9, I run out of standard decimal digits and I switch to alpha characters, A, B, C, D, E, F. So for example here, B is 11 decimal, or 1011 binary. You got to memorize these. The quicker you memorize these, the better off you'll be. Here's the table in all of its glory. Once again, we generally represent a binary using 4 digits, 4 bits. It's for reasons you'll see later. It's very effective. You'll see that in the next chapter. Lastly here, there are some important powers of 2. Basically speaking, here's your powers of 2, here's your powers of 2 minus 1. These are very important numbers. The quicker you memorize these, the better off you'll be. Once again, you'll memorize these anyway because you'll use them so much, but if you just kind of stare at them for a while, they make a lot of sense. Here are your 2 brought to the integral powers. Here's the associated decimal number, and here's the associated hex number. So what's interesting here is the hex. It's 1248, 1248, 1248. You can see this repeating pattern, 1248, and then it shifts over 1 digit, etc., etc. Very, very nice to work with. So here is the binary numbers raised to integral power, subtracting 1. Here's the resulting decimal values. These are very important values. And here's the associated hexadecimal values. So once again, I could have put binary in here. I just didn't want to go that far. It would have really messed this thing up. But check it out. These numbers here in hexadecimal represent all ones. Now these numbers here represent all zeros except the leftmost digit, which is a 1, leftmost bit in that case. Again, important numbers, you'll see these numbers in these two columns come up all the time. Simply something you want to